Hey everybody, welcome back. We're in section 8.3 today. We're looking at the algebra of functions, which I wish I could say it sounds more fun than it is, but you're probably going to maybe not be in love with this section. I hope that you don't find it too challenging though. I think this is one of those sections where if you really pay careful attention and you get in some good practice, you're gonna have no troubles with it. But if you kind of just gloss over it real quick, this section will really just give you a bad time. So there's two main ideas in this section that we need to look at. The first being, we're going to revisit the idea of domain. And we've kind of talked about domain with relations, where we were just literally picking off the first value listed in a coordinate. And then we got a little bit more involved with it when we started looking at graphs in the last section. And now we're going to extend the idea further to where I'm going to give you a function, I'm going to give you an equation, and I'm going to say, what is the domain? And so I'm going to show you, now, not for any function ever, right? We're not ready to do that, but just in a very specific set of cases, I guess, is what we get to deal with. So we'll get to find some domains of functions, and then we're going to mess around with the main idea of the section, which is how to deal with algebra as it pertains to functions. So basically what that boils down to is addition, subtraction, multiplication, and division of functions. So are we ready? Let's do this. So in the first portion of this, I want to talk to you about how to find domains of functions. So your domain is, of course, the x values that you are sort of permitted to use safely and plug in and know that when you plug this particular x value into a function that you are going to get back a y value in return. So there are certain cases, and you've kind of seen some of this before, actually. There are certain cases that when we plug a number into a function, bad things happen. So for example, in the last chapter when we studied rational expressions, if you plug the wrong number into the denominator, it was possible the denominator could turn into 0, and then the whole thing became undefined. So that's not something obviously we want to deal with. So we want to avoid that. Okay, so to find domains of functions, there are basically three cases here that I want to make you aware of. So in case number one, we're going to talk about polynomial functions. Now, these functions are the kind that you're most familiar with, right? These are the ones that look, I don't know, I could write something like f of x equals x squared minus 5x plus 2 would be a polynomial function. And the thing is, like, okay, with polynomial functions, how do I deal with the domain of them? This is the easiest one ever. If you know that you have a polynomial function and you're asked to find the domain, every single time, ready for this? This doesn't happen often in mathematics where we can say it like that, but every single time the domain is just going to be all real numbers, right? Any number in the world that you can think of, any real number you can plug into this thing, you're going to get a y value in return. Everything's going to work out nicely. So our domain for a polynomial function, we could say it in words. We could write it out as all real numbers. Another way we could describe this would be to use that interval notation. And so we could write it from negative infinity to infinity is how we would describe all real numbers. And then there's actually a symbol in mathematics that we use to describe all real numbers. And it looks like a capital R, but like it just has an extra sort of, instead of like when you draw R, you would normally start drawing R with like a vertical line, right? Well, when you do the symbol for all real numbers, you just do two of those vertical lines next to each other and then just proceed to make the rest of your R. And so that symbol right there stands for all real numbers. So any one of those would be perfectly acceptable to write down. You don't have to write down all of them. One is more than enough. So for polynomial functions, the domain is all real numbers. There's no work that needs to be done. It's literally just you recognize the function, you remember what the domain is, and you write it down. Okay, can't make it easier than that. Now, what about case number two? Well, in case number 2, we're going to talk about rational functions. And we spent a lot of time looking at rational expressions in the last chapter. So this should be somewhat familiar. So I could say something like, f of x is equal to x squared minus 8 over x plus 4, let's just say. That is a rational function. I know. I'm tired. I don't mean to be all with you this evening, but it's been a long day, right? It's been a long day, and it's into the evening now as I record this. So if I'm sighing or if I start yawning, my apologies. Anyway, the rational function here, how do we deal with its domain? Well, we deal with the domain here in the same exact way that you would deal with finding those excluded values of rational expressions from before. So remember, the procedure for that was take the denominator and set it equal to 0. So denominator in this case is x plus 4. Set that equal to 0, and then solve it for x. So to solve this for x, what do I need to do? I just got to subtract 4 on both sides. And I get x equals -4. Now before, in chapter 7, we would have said, okay, this answers the question of what values do I need to exclude? This doesn't answer the question of what is my domain? My domain is not x equals -4. My domain is every number except that. So when I want to write down the domain here, I've got to be careful how I say this. I could say all real numbers except x equals -4. That's one way you could say it. How else could you say it? You could say x is not equal to -4. That's probably the most convenient way. That's the quickest way to do it. And then you could do it this way. You could use the interval notation, but the interval notation is going to look a little weird here. It's how do we write interval notation to show everything but one single value? You would go from -infinity to 4, and you'd put parenthesis on the 4 because we're not including the 4. Excuse me, -infinity to -4, sorry. -infinity to -4, and then you'd put a parenthesis on the -4 because we're not including that. And then you would then pick this up again at -4 and head off to infinity. So you'd actually have to kind of write 2 intervals to represent the situation. And when you write 2 intervals using this interval notation, you then have to put this U in the middle of them. It's a union symbol. And it's okay if this is brand new to you. We haven't covered this yet. We will cover this idea in the next chapter. But for right now, if that's a little bit different or a little too weird for you, just use one of the top 2 choices that I said. Either probably the middle one there, x is not -4, is certainly fine. Okay, polynomial functions, just all real numbers. Rational functions, the rule is set the denominator to 0, solve it, and then any numbers you get do not get to be part of your domain. And then finally, the third case, and we'll deal with this one more in the future as well, but just to kind of get us started with this idea a little bit, it's for a radical function. And we'll get to radical functions, I believe, in chapter 10. So still a little ways to go. But a radical function you could take, let's just take a very basic one. F of x is equal to the square root of x. Oh, and now it's not writing. So 1 second. Let's reconnect. There we go. Now we're back. Okay. So f of x equals square root of x. And the rule for square root functions is that you have to have a number no less than 0 underneath this square root symbol, or underneath what we call the radical symbol. We can take the square root of 0, it's just 0. But if we try to go less than that, bad things happen. So we can't deal with those cases, at least not yet. So what we're going to do is we're going to take whatever's underneath the radical and we're going to make that greater than or equal to 0. So we're going to have to use an inequality. And again, that's another thing that we haven't kind of broached that subject of inequalities with the content from this class yet, but we will get to that later as well. So for right now, here's what I want you to do. When you're going to deal with the domain, if it's for a radical function, take whatever's under the radical, in this case just x, and make it greater than or equal to 0. And that's it. Now, if there was a little bit more involved, like if it was like x, say x plus 1 is greater than or equal to 0, then just move the 1 over, right? Or if it was 2x minus 3, then just add the 3 and divide the 2, right? You just move the pieces over. I'm just kind of giving you the general kind of basic case here of just x. And again, don't worry on these too much. You're not really going to encounter these yet. This is just more of a preview than anything else. So your domain is x is greater than or equal to 0. Or if you wanted to express that in the interval notation, that would be from 0 with a bracket on it up to infinity. Okay, so there we go, and we'll deal with these. We'll deal with these in a lot of different ways, but primarily my main concern right now is, do you understand case 1 and case 2? And if you understand those, then we're good to go. All right. Okay, hopefully there wasn't a weird pause there for too long for you. Had to pause the video for a second, but we're back. So just finished up talking about how to find the domains of a few different types of functions, and now we're going to look at the main topic of this section, which is the algebra of functions. So with this, what we're going to do is I'm going to give you the 4 basic operations that you're going to use: addition, subtraction, multiplication, division. I'm going to show you this kind of different notation that you're going to see for this. And then I'm going to show you what that notation actually means, and I'm going to tell you how to work with it. And then once we've established all of that, then we can work through some examples of how to deal with this stuff. And hopefully by the end, you'll feel pretty good about it. So the first thing that we'll look at is to do with the sum of 2 functions, or adding 2 functions together. And when we go to sum 2 functions together, let's just assume that for all of these right now, just in very general terms, the functions we're dealing with are f and g, right? Let's just give them those letter names. The letter names don't really mean anything, but that's pretty standard, so that's what we'll use. So you may see in your work as you're practicing something that looks like this. And the way you would read that is f plus g of x. Okay, so that's f plus g of x. That's how you read that. The thing that you need to know here is that even though you see stuff in parentheses, this in no way is describing multiplication. All right, we are not multiplying x by these variables of f and g. What this really means, when you see this is the same thing as if you see this, f of x plus g of x. It's literally just adding 2 equations together, or adding 2 functions together. And by adding these functions together, you're going to create some new function. Now, the reason why you would see it written as it was to start, where f plus g were together in parentheses, that's just for convenience. That's just to kind of consolidate the ideas down. That's one of the things that, if you haven't picked up on already in math, that we do that a lot, right? Where we try to find more creative ways of writing something that will mean the same thing as something else, but maybe it's just far more condensed down. So when you see the f plus g in parentheses next to an x in parentheses, that f plus g of x, it just means take f of x, add it to g of x. So how are you going to do this? How are you actually going to add the functions together? It's simple. The procedure is just going to be to combine like terms. So if you know how to combine like terms, you already know how to do this. In fact, you've probably done stuff very similar to this, just haven't seen it with this notation before. Okay, so that's our first operation for addition or for taking a sum. The second one is going to deal with taking a difference or in subtraction. And it's going to look very, very similar to the one up top, except it would be f minus g of x. And what does that actually mean? This actually means to take f of x and subtract g of x. So how do I do that? Well, you just combine like terms. Okay, easy enough. What else do we have to do? Well, the third option is dealing with a product. So that would be the multiplication side of things. And the sort of condensed version of how we would write the multiplication of two functions would just be to write f times g like this of x. And what does that actually mean? Well, it's just f of x times g of x. That's what it means. Now, how are we going to do this when we're multiplying? This one's going to most likely be one of these two. It will be distributive property or it could be something like FOIL. Those are the two ideas, which again, good news, because for the first two cases of sum and difference, it's combined like terms. You know how to do that. In this case, distributive property and FOIL, you know how to do those already also. So that's pretty great. So even though this is kind of a new thing, it's going to rely on a lot of stuff you're already good at. Okay, and then finally, we have the quotient. The notation is going to look like this: f over g of x, or f divided by g of x. And what that really means is that you're taking the function f of x and you are dividing it by g of x. Now, what's going to be the procedure here? Well, when we're dividing functions like this, this looks like something we would have dealt with in the last chapter. So really, all that can be done here is potentially, you could see if it will simplify. But if it doesn't, then there's really nothing to do. You basically just leave it in that form. Okay, so now that we have the general idea here, let's just run through some examples of how to practice all this. So for our example here, we're going to let f of x be equal to x squared minus 3. And we're going to let g of x be equal to 4x plus 5. All right, and let's just, at the very least, we're going to run through these four things, 1, 2, 3, 4, up here. But I'm also going to mix in some other things, some other just variations of what we're doing here that you'll be asked to do that will just require no more skill than what we've already gone over. Okay, so in the first one, in part A of this example, let's find f plus g of x. All right, so let's suppose that we were asked to figure this thing out. All right, so what I would suggest that you do when you're working on these is to first just remind yourself of what does this thing mean, right? So this means to take f of x and add it to g of x. Okay, that's all fine and good. So if I want to find what f of x plus g of x is, I need to substitute in these functions. So instead of writing f of x, I'm going to write x squared minus 3 because that's what it's equal to. So x squared minus 3, and then I'm going to add this to my g of x function, which is 4x plus 5. And then as it says up top there, just combine like terms. So looking here at the potential like terms that can go together, it's just the constant terms. So we're going to get an x squared. We have a plus 4x. And then if you take that negative 3 and add it with the 5, that's just going to give you a positive 2. And this represents your solution. So x squared plus 4x plus 2 is what you would get if you were to add those two functions together. Okay. So literally just combining like terms is all you're doing. All right, let's not jump into subtraction just yet. What if you're working on some homework or you're working on some review or you see this on an exam or something and you get a question that follows up the one we just did, but instead of saying f plus g of x, it says f plus g of, I don't know, let's say negative 2. So what this means is not to multiply anything times negative 2. It does not mean multiply by negative 2. What this is telling us is everywhere there's an x, go ahead and plug negative 2 into it. Well, we've already added these together, right? So I don't need to add the functions together again. I've already done that. So I'm basically just taking my answer from part A, and everywhere there's an x, I'm just going to replace it by negative 2. So this would be negative 2 squared plus 4 times negative 2 plus 2. So I'm going to put all this together, and this is going to turn into, let's see, negative 2 squared is 4. And then I'm going to get a minus 8 and a plus 2. And when we work all this out, we end up with, we get negative 2 right back. How about that? It doesn't always happen. Picked x to be negative 2, and the output of it is also negative 2. Cool. All right, so when you see the number next to the f plus g, just plug that number in for x. That's all that means. All right, so hopefully you will not overthink it and think, am I supposed to multiply everything by negative 2? No. It's not that. Just plug it in the negative 2 and you'll be fine. All right, part C. Let's do f minus g of x. So if I want to do this one, the subtraction ones are always just slightly more involved just because we have to be careful with subtraction. It's not as convenient as addition. So when we go to subtract these, remember what this means. It's f of x minus g of x. So f of x, we already know what that is. It's x squared minus 3. So it's kind of starting off exactly the same as part A, but now we're subtracting. But the thing is when we go to subtract g of x from this, we're subtracting all of g of x, not just the first term. So the thing to remember here is some parentheses, and we're subtracting off a 4x plus 5. And the parentheses just remind us to distribute that negative into both of these terms. So what are we going to end up with here? When we distribute that negative, we have x squared minus 3 minus 4x minus 5. And then when we go to combine like terms, we're going to get x squared minus 4x and then minus 8. So that's what we get from combining the negative 3 and the negative 5. All right, so there's a subtraction style problem. And then what if, let's suppose that in addition to that, just for some practice here, we were asked to identify what is f minus g of, I don't know, let's pick something fun to use. Let's use 0 this time. That's a fun one. So does it mean multiply the function by 0? No. It means everywhere there's an x, plug in 0 in its place. So same thing, we're going to take the answer we just got in part C, and everywhere there's an x, we're just going to replace it by 0. So it's going to be 0 squared minus 4 times 0 minus 8. And those first two pieces just go away, right? 0 squared minus 4 times 0, that's nothing. So all you're left with here is a negative 8. Okay, so there's addition, there's subtraction, and there's how you handle plugging in a value. Let's look at multiplication. So let's say we were asked to find f times g of x. So just like before, just like with addition and subtraction, let's just remind ourselves of what this means. It's to take the function f of x and to multiply it by your function g of x. So in this problem, when we go to multiply our functions, we're going to want to use parentheses on both. So it's going to be x squared minus 3. And then we're going to multiply that by 4x plus 5. So we're going to multiply these two together. And if you look at what it says next to the product, it's distributive property or, and it's not me. I know depending on how this is. There we go. It's distributive property or FOIL. So in this case, that's precisely what we're going to do. We're going to use our FOIL to help us to figure this out. So if we FOIL this thing out, we're going to get 4x cubed from multiplying these first two. And then when we multiply the outside two, x squared times 5, that's a plus 5x squared. The inside pieces become a negative 12x. And then we get minus 15 when we multiply the last two. And then under normal circumstances with FOIL, when it's kind of like, you know, an x plus 3 or x minus 2 or anything like that, there's going to be like terms in the middle. But this case, we're not going to have that because in our first set of parentheses, we had an x squared. And in our second set of parentheses, we had just a plain old x. So there are no like terms to combine. So this would be our answer, like so. All right. So then what about dealing with a value here? What about trying to find f times g of, I don't know, let's just do positive 2 this time. Okay, couple of different ways you can do this. So for example, let's suppose that in this problem, you were not asked to do part E first, and you were only given part F, and it said just find f times g of 2. So does that mean that you actually have to multiply everything out first like we did in E and then plug in the 2? No, you can do that. And if that's what you're comfortable with doing, then that's okay. But another approach to this is to recognize that what this really means is you're taking f of 2 and you're multiplying it by g of 2. And so instead of multiplying the functions together and then plugging in the 2, you can actually plug in the 2 into the functions first and then multiply their results together. So for example, f of 2, let's just do some little side work below here. F of 2, that's equal to 2 squared minus 3. If I plug 2 just into my function f, and that would be 4 minus 3, which is just 1. And then if I did the same thing for g, if I was like, okay, well, what is g of 2? Well, that's going to be 4 times 2 plus 5, which is 8, plus 5, which makes 13. So instead of having to plug in to the end of this thing, I can just recognize that, okay, f of 2 is equal to 1, and g of 2 is equal to 13, and 1 times 13, well, that's just 13. So would it work the same if we did it the other way? Let's check. Let's just see. I want to convince you, because maybe you're kind of scratching your head here being like, wait a minute, why wouldn't you just plug it into the answer from part E? Like, couldn't that just be the same thing? Well, let's see. Maybe it is. I think it's going to work. Let's try it. It's going to be 4 times 2 to the 3rd power plus 5 times 2 squared minus 12 times 2 minus 15. So 4 times 2 to the 3rd. Well, we got to do 2 to the 3rd power first. So 2 to the 3rd would be 8. And then 8 times 4, that makes 32. Plus, here we would have to do 2 to the 2nd power, which makes 4. And then multiply it by that 5 in front. So that's 4 times 5 is 20. And then minus 12 times 2. So minus 24 minus 15. And this is going to be, let's see, we're going to get 52 minus, well, that's the equivalent of minus 39. And sure enough, it works out the same. So there you go. You're going to get 13 in either case. So basically, it's kind of up to you. If you were not asked to do part E first and you were only asked to do f times g of 2, then you could do it the way I showed in red by just plugging 2 into each function beforehand and then multiplying your answers. Or if it's just easier for you, you could do what we did in part E and multiply them out, do the FOIL, use everything in terms of x, and then plug in your number. But it's entirely up to you. I'll leave it at your discretion for how you're going to be comfortable resolving those problems. Okay, this has got to be the longest problem we've ever done. Well, at least maybe not the longest problem we've done, but certainly with the most parts I think we've ever had so far. So in part G, what is f divided by g of x? What is that going to be equal to? All right, well, we've kind of got the idea now with as much of this as we've done. We know that that just means f of x divided by g of x. And so I just need to write down my functions as a fraction. So my f of x function is x squared minus 3 over my g of x function is 4x plus 5. Now, numerator and denominator are completely factored out. So there's nothing we can do with this one. So that is your answer. So the division ones, most of the time, are going to be the easiest because there's really, unless you can simplify it, there's not going to be anything you can do. Now, don't get too excited about the division ones just yet because there's going to be another question that's going to be asked pretty regularly as it sort of relates to these division ones. And it's not something nice like just plugging in a number. It's something like this, where it's going to say, the domain of f over g. That's what it'll say in the problem statement. It'll say find these things, and then it'll say the domain of f over g. And you're like, the domain of what? Like how do I deal with that? Well, what you need to do is you need to remember that at the very beginning of this lesson, we talked about how to find the domain of a variety of different types of functions. And in case number 2, we said that if it was a rational function, which is exactly what we have here in part G and H that we're working with, if it's rational, take the denominator, set that equal to 0, and then whatever answer you get from that, that number is not in the domain. All right, remember we did it. Let's just scroll back up to the top just so I can remind you. Right here on the right-hand side, case 2, rational functions, right? We took the denominator, set it to 0, solved it, and we said the domain was all real numbers except for that value. All right, so we're basically just going to do that same thing, but for this function instead. So the function that we're using, we found it up in part G. So the denominator that we have is 4x plus 5. So take your denominator of 4x plus 5 and set that equal to 0, and then solve it for x. So to solve this for x, we would subtract over the 5 on both sides. We would get 4x equals negative 5, and then just divide both sides by 4. So you get x equals negative 5 over 4. Now this is the excluded value. So this is the number that we don't want. We want everything but that one. So we would answer part H of this question by saying the domain is going to be, the easiest way I told you to write this was to take x and say it can't be negative 5 over 4. So any other number you want to plug into that function up there in part G is just fine. You just can't use negative 5/4 because if you did, it would completely zero out your denominator. Okay. Let's see. What else could we look at that might be at all challenging? So we kind of went through just a real quick, we did addition, subtraction, multiplication, division. We've talked about how to plug in numbers. We talked about the domain thing that's going to come up. Oh, I know one we can do. Okay. We're going to change our example. Right, so we're going to be done with these functions, f and g. I'm going to give you a new set of functions. So let's get that stuff out of here. Let's make a new example. And in this example, we're going to let f of x be equal to 4 over x, and g of x is going to be equal to 3 over x plus 2. All right, so there's your two functions. Now, here's what we're going to be asked to do with them. It's going to be pretty quick on this one. I'm not going to run through everything on these. The first thing in part A that we're going to be asked to figure out is what is f minus g of x. And then in part B, we're going to be asked to identify the domain of f minus g. Oh, and it stopped writing again. All right, hold on 1 second. Share the screen. There we go. And there we go. Okay, sorry about that. So in part A, we want to find f minus g of x, and then in part B, the domain. All right, so let's work these out. So we'll start with part A. So if I want to find f minus g of x, well, we all know that that means really just f of x minus g of x. And I just want to subtract the two functions. So if I just wrote the functions next to each other with a subtraction sign in the middle, it would be 4 over x minus 3 over x plus 2. But we just learned in our last chapter that the only way we can subtract these is by coming up with a common denominator that we can use. So in this problem, it's pretty nice, right? I think if you kind of, all things considered based on some of the stuff we did before, the LCD here is going to be easy to find because both denominators are already factored and there are no repeat factors. So the LCD that we're going to use here is just x times x plus 2. So that's what we need to get in the denominators that we have here. So let me take 4 over x to start with and say, you know, what do I need to do to 4 over x to get x times x plus 2 as its denominator? And so I hope you would all recognize that we would need to multiply top and bottom by x plus 2. And remember how this works. For numerators, we always distribute. So this is going to be 4x plus 8. Okay, so there's the first fraction is now taken care of. Now the other one, the 3 over x plus 2, what do we have to do to that one to get x times x plus 2 as our denominator? And on this one, we would multiply top and bottom by x. So your numerator, when you multiply across, is just going to be 3x. Okay, so now we can subtract them. So we're going to have 4x plus 8 over x times x plus 2, and then minus 3x over x times x plus 2. And what is this going to be equal to? Well, if we subtract, we have a 4x take away a 3x, so that's 1x, and there's still a plus 8. And then we have this over our denominator of x times x plus 2. Okay, so there's our solution for what we get when we subtract, right? So just kind of, you know, reminding us of how to deal with, you know, common denominators. This stuff kind of spirals back through, so it's kind of helpful to keep it fresh in our heads. But now I want to find the domain of this thing. So remember the process, it's fraction. So the way you find the domain is to set the denominator of this equal to 0. So the denominator here is x times x plus 2, and I'm going to set that equal to 0. So this is zero product property here, right? We take each factor and set them equal to 0. So our first factor is x, and we're going to set that to 0. Our second factor is x plus 2. We set that to 0, and then we solve. Well, the first one's already solved, right? We get x is 0. And on this second one, if you subtract over the 2, you get x equals -2. But remember how this works. this doesn't mean that the domain is x equals 0 and x equals -2. It means the domain is all real numbers except for these two. So it can't be those values. So your domain is going to be x is not 0 and x is not -2. We'll learn a cooler way of writing that using the intervals with some union symbols later, but for right now, we'll just leave it, like this. Okay, I think that is about as sort of as messed up as these can kind of get, where you have to really kind of bring on board some skills you learned in the last chapter. But overall, the main thing is, and I'll kind of scroll back up to where this kind of started. The main thing is this right here, is do you recognize, what this new notation actually means? So when I say to find the sum, when I say f plus g of x, my expectation is that you're going to know immediately that I'm saying, oh, f of x plus g of x. Or if I say find f times g of x, that oh, that's f of x times g of x. If you know this stuff here in this highlighted box, then the rest of this will be okay, because it's just, like I've said before, it's just building on like prior knowledge. So try not to get too worked up by this. Try not to overthink this stuff. If you are having trouble with it though, let me know right away. We don't want to let this sort of sit and linger and have you be confused. All right, that's going to do it for this one. I'll see you guys back here next time.